Alright, so this is the video for the FEM2 lab, and it's actually I'm recording this right after the first video. This is a really short process, so I'll just go ahead and start doing this. And actually, let me take a look at the schedule. Okay, so the FEM2 lab is mesh. It's also mesh. So in this lab, we will generate the whole mesh for the handles and the mesh for the blades. Okay. So first for the 2D shell, we can hide the polygons. We don't need to deal with them. Then we can hide the shell on the blade. So we have this two piece of handle, half. Then what we're gonna do is we can reflect them into the other side. So we're gonna insert element, then copy and reflect. Okay, so there's really no, you can't pick the whole thing. You really just need to use the box to select everything. So that's why before you do this, you need to hide whatever you don't want to reflect. Okay, just show the mesh you're working with. And the reflection plane is, as we know, it's X and XY plane. So we're gonna choose ZC here. That's your symmetry plane, and then say OK. Alright, so that looks like the real thing now. We are not done yet. Okay, so every time you reflect a mesh on the symmetry plane, you have one edge from the top, the edge from the top, and the edge from the bottom. That means this edge is duplicated. You have two edges in the middle of the supposedly should be a whole piece of mesh, and actually now it's not a whole piece, it's two pieces. They're separate. At the same point, for example, here you have two nodes. Okay, you have a node on the top from the top and another node from the bottom. So in the physical perspective, it's like you cut this thing in half, and we don't want that. So what we need to do is we need to merge the nodes. So here we have a command. Usually we use that right after the reflection. So you want to eliminate the duplicated nodes. And we turn this on. Okay, duplicate nodes. And then you pick those two pieces of mesh. And you can see right away, those are the duplicated nodes within this tolerance. Okay, because they're coincident, so basically they will be inside this tolerance. And we have a option here is merge nodes. So if you click merge nodes, it'll merge those together. And now this is a single piece of mesh when you do a simulation. Even though in the tree it says mesh and a reflected mesh. Okay, so when you do a simulation, this will be considered as one piece. And how do we tell if this is a one piece or not? We have a examine tool. It's called element edges. Okay, remember I didn't merge the node on the left side. So let's see what happens if we pick all of them, and we will generate the element outline. And that's pretty much the external edge of a mesh. And the one on the right side, you don't see an edge in the middle, right? That's only the edge that's exposed to the outside that has an edge. And if you look at the left side, we have a blue line in the middle. That means this is the external, or this is considered as an external edge for the mesh. And that means this one is cut in half right now. So again, we need to do duplicate nodes, pick those two pieces and merge them. Okay, so now I'm pretty sure they are what they should be. Okay, then we're done with the handle. Then let's turn on the polygon for the blades. Okay, this is really simple. You basically just need to do a 3D texture. Okay, here we use texture 10. It's a parabolic texture. It will not be too stiff. And the size is different. The size is 0.1 inch for the 3D texture. Okay, again, that's 0.1 inch. That will be written in the slides, which I don't have now. So 0.1 inch and texture 10. Let's get one first. Okay, usually the parabolic will have double the number of the nodes in the element. Then it will triple or quadruple the time that you need to calculate the model. So you want to reduce the number of textures as much as possible to save some computer resource. Okay, then the other one, we can actually put them in the same collector. Okay, so here usually it says auto create, so that's why every time you create a mesh, it'll automatically create a collector. But you can turn it off and put in the one you already have. Okay, so this way you don't get a lot of different collectors. Alright, so that's the 3D texture for the blades. You can also change color if you wish. And I think the schedule is way too little for lab 2. Then probably we can proceed to the FEM assembly. Alright, the FEM assembly, well, maybe not. Let's give them material first. Okay, so we know everything should be steel right here. Everything should be steel, and we will put a piece of wood or nylon between the tip. So first, let's create the piece, nylon piece or wood piece. So we will create a node between nodes, okay, between this tip to that tip, and they should be on XY plane. Then that's a node between them. Okay, let's take a look at F8. So they're aligned. Then here we're gonna insert a C bar. Insert an element, create a 1D C bar element, and from this node, oh oops, you want to pick the right node to here. Then the second section, okay, be careful here, you want to put in the same collector and add to existing mesh, which is this piece. Okay, for this option it's not necessary because they share a node, so no matter which mesh you put in, there's still a welded connection here. It's just for the ease of management in this tree. Okay, so we have this nylon or wood, whatever you call it, in this collector. And if you notice, we share a node here. So the C bar and the blade actually shares one node here. Does that mean this is a welded connection? Well, no. The thing about 3D texture is 3D texture doesn't have degree of freedom of 4, 5, 6. So that means if you transfer or if you rotate this C bar here, it will not get transferred into the 3D texture. So basically this joint here, it's like a ball and socket joint. Even though they share a node, but the 3D texture is missing degree 4, 5, 6. So you cannot transfer any rotational degree of freedom into the 3D detacher by just single node. There's ways you can transfer them into the 3D detacher, but this way it's easier than you to create a joint here. You can simply just go straight into 3D detacher. That'll form a ball and socket joint. Okay, so that's for the C bar here. Then I guess we'll do some material and thickness for the 2D, and then next lab we'll come to the FEM assembly. So the thickness for the handles is 0.08, and the material is steel. Just pick steel from the library. And notice we use we just modify the property for P shell 1, and that's the same for P shell for the other handle. So you don't have to assign any material or thickness for P shell 2. You can simply use P shell 1 for the collector, for the other collector for the handle. Okay, so thin shell yellow and the red, they both using P shell 1. Okay, so P shell 1, the same property. Then the blade is a different thickness, so we need a different blade collector and different property. And it's also steel, but the thickness is 0.26 inch. Okay, so here you can't really see the thickness of the 2D shell, and you don't know that 0.26 goes from the 2D shell up or bottom or symmetrically. So there's one way to check that. You can right click and add a display for the 2D shell. Then we can enable the thickness display. Okay, if you say apply, you can see the thickness in the view. Okay, so by default, the thickness of a 2D shell goes symmetrically. Your shell is in the middle. That's why we need to find the mid surface of the handle. This way, the thickness, if you just mesh the top surface of the handle of your 3D geometry, actually your mesh will be offset a half of thickness. So that's the reason we use mid surface. All right, so that's it for the second video, second FEM lab. Next lab we'll just do assembly, spiders, C-bars, and bushings. Then that'll connect everything together. All right, thank you very much.